Okay, I want to bring your attention to this. It's some old studies, and this has helped you visualize rebar under stress as it's bonded with the concrete around it. Let me take a shot of this and work from it. So what you're looking at is here's the rebar, right? And these are the fractures that propagate out once this rebar is being stressed, strained, pulled on. And how's it being pulled on? Well, let's use a cantilever. So we have a cantilever here. Here's a wall system. And so it's unsupported here. No supports here. None, right? No. Okay. Oops. Do that again. And let's do that again. So there are no supports there. So you can imagine what location I might be talking about roughly. Now, looking at this rebar, this is how the finite element programmer describes it. Okay. So as the concrete is surrounded around the rebar is here. I'll get us zoomed in a minute, in a moment. So let's zoom in on that. So you can see the rebar there, and they actually refer to it as combed like concrete and teeth, deformation of teeth. All right, it's the deformation of the rebar. They call it teeth in their dialect whenever they made this paper. And I'm just going over this paper. I've gone over it before. If you look at it down below, it shows a cone shape is basically what they're trying to say. I'm not in total agreement, not total disagreement. I'll show you what I've learned through my rebar pull-out test. Is at one point you're climbing, and so here's your scale. You're pulling on it, and say you get right here at whatever it may be, 30 newtons, right? Kilonewtons, 16 kilonewtons, 11 kilonewtons, whatever it may be. At some point, your chart, you start going down on your chart. At some point, you start gaining value, and all of a sudden, it just first it tops off. It will level off. Okay, and then you're like, oh, okay. So now you expect the crash, right? The drop off now is showing it's released. But that's not true. After you get that level off, your max happens, and then you get this level off, you'll get a climb again. This climb, I believe, is happened because these micro fractures in here, larger than micro, uh, they start filling in with debris. They've now dammed up the area here with shim-like debris, the concrete that they've ripped apart with the deformed rebar. It's stacked up, and then you'll get a reclimb, and it won't be much. It might be 2 kilonewtons or something like that, and then from there it's just downhill. It's done. You're toast. So you've now lost bond. You're just a fake right here, rather. So right here, this is just a fake increase. It's lost bond right here. So your max is here. Your margin of safety is wherever you decide it would be. Down here. And interesting rebar dimensions. The number 4 rebar, half-inch rebar, actually will give you a better result than, I say, a number 5 in the same psi concrete. The smaller rebar gives you better anchorage. To be explained, never. Looking at the internal now of this, I'm going to take a shot of this, and we're going to use it as a test sample cube of a core sample. I want you to think of this is the rebar, and there's the splits that you see from the rebar ribs going all around. The teeth of the rebar is this, as this document says here. Those teeth create the fractures like that. These are fractures, those little green lines going out. They're fractures, all right? So these are fractures you're looking at. And it says internally cracked zone. Okay, so internally cracked zone, as it states, here. And this is the uncracked zone, it says. So you won't, if this is concrete cover, and you start seeing if it's thick enough concrete cover, you won't see the uncracked. This will be taking place, but you won't observe that. But you might observe a fracture in the deck, and you can't figure out why. Just to say the rebar is going this direction, and anchored over here at this side, and out here is a cantilever, let's call it. So cantilevered out here. So your anchors are here and here, and the bond of the concrete is the cover. It's all around it. The cantilever, being at the ends, at the furthest end out, has the greatest deflection, the greatest stress on this deck. Now imagine that. So it's on as it works its way back. So here it is here, and here's the steel. As it works its way back, this section is strained more so than this section back here. It's not directly pulling on back here yet, because it's got a lot of support between there, a lot of rebar support between there. So if it fractures, if you see a fracture there, well then it strains the next zone back, if you will. Now this becomes more of an anchor point, and this zone here becomes an anchor point, but this becomes the anchor point on the other side. Not this yet. And you would look on the underside of the deck, and you would look for fractures underside. To look at these indicators, and also opening at the top here. So openings up here. But the good news is something like this cantilever deck that I'm theoretically talking about, wink, wink, is that this part of the cantilever deck is not failed for the most part. There are in a few places, yes. So that now let's put our steel in here. Our steel goes back internal to the building. Let's get rid of that. Let's do this again. So let's do this. So here's our steel, and then there's our concrete with a little bit of cover. And let's go like this and back to the structure. And there's this section here. So let's, how do I do this? Let's do this. This part of the concrete is still solid for the most part. There's some that's spalled off. So this becomes an anchor point. So this is an anchor point. And back here is internally is an anchor point. As it stresses, this anchor point is what on a cantilever is the part that wants to have the greatest force, that wants to go down. So 10 pounds out here puts your greatest stress on the deck than 10 pounds right here. Okay, so 10 pounds here puts your greatest stress on the deck out further out than closer in. All right, so it's a cantilever. You're holding a weight further away from your body, if you will. You know how it starts to get. So we have this top concrete spalled off the deck. All right, spalled off the rebar. But the rebar is still engaged. It's still there. You see it exposed. It's still there. It's still in this anchor zone, because for the most part that's secure. And it's still in this anchor zone. So even though the rebar is exposed, the cover's removed. The rebar is still, as the cover's removed, where the cover grabs again, which might be back closer to here. That's your anchor point. And further back, I hope the development of the rebar, assuming the development of rebar goes further into the structure. So you can see you've got an anchor here and an anchor here. The deck wants to rotate down. It can't, because the steel is still there. It goes in tension like a cable, if you will, but it's steel. So it's a post-tension rod at this point, and the anchors of the rods are here and wherever it's last connecting here. And the deck wants to rotate down, but it does what to this bottom zone, the bottom zone of the concrete. So this bottom zone of concrete is still existing. It tries to rotate down, but that's a force back towards the wall. That puts this in compression. I know they tell you concrete is in tension in the bottom, but now you visualize It's not true. It's most of it's a lie. Actually, cantilever, the top part is the tension part, and this part is compression back to the building. So you got compression back to the building. So you look underneath the deck and you look for defects that would look like compression spalling, blowing out. I'm not talking about there's some skim coating that they did there over the years that had no chance in hell on staying. So I can't evaluate skim coated material because it's skim coating. It's like putting a blanket over it. I can't see through a blanket. All right, so we can't see what's really going on with the skim coating, but we can look at the top rebar and we can see how it's behaving, such as ringing it, grabbing the rebar, and seeing how tight it is. Is it taut or is it not taut? If it's not taut, there's some redundancy going on here as the rebar comes out from the structure, being here, the structure. Some of it's exposed like that, but we have it anchored out here. But they also have a lot of rebar that's going the other direction. I'm going to do that, cut into my rebar with the white. And that rebar is acting like a transfer steel there. It's not at the very top, a little bit below it, but I did see some rebar going the other direction. And it's helping recapture as steel goes down here on the outside of this, let's say this bad area here. Call it bad if you like. The top cover is missing. Now it loses the ability to be bonded with the concrete below, so it's not there. So it becomes anchor points, and it's more like a PT now, post tension bars action going on, as opposed to what we see in the drawing here, where it's fully developed. So initially the stress happened, and as this Gatto study 1971 shows, the concrete was stressed circularly, right, radially, like that, as it was being stressed, and this top section here was broke bond. They also have salts that they apply there over the years, the tenants, I'm sure, and whomever else, I don't know. And the salts get down there and they do expansion and they expose the steel to air. Salts are very corrosive. How do we know salts are corrosive? Buy a car from New Jersey by the shore and you'll find a car that's not worth keeping. That salt air will tear it up. Well, if you create a slurry, salt water and water that melts snow, etc., you create a slurry and you put it on the steel, you created your automobile in your New Jersey car, your typical New Jersey car, all rotted out. So you start rotting out this steel and it flakes, all right? And also the steel design, I don't know what this steel design is, maybe the shelf life on it exposed to those elements create that accelerated process. But I see a lot of areas that are not cracked and not disturbed, so the salts didn't get to those areas. So that's good news, and for the steel, saying that, okay, it's not just the steel expanding because of a bad mix design, because it would be everywhere, and you wouldn't be able to figure out why is it, you wouldn't be able to say salts. Plus, we see the pitting that takes place when you apply salt to concrete, and a lot of that pitting is there, present in this structure. So the bar now is acting like a PT bar, post tension bar. You've got your anchorage back here wherever it's good, and then out here we have for the most part we have the outside good there. This becomes a PT bar. So I want you to think of that, and remember the bottom of the concrete matters. That compressive forces if it's trying to rotate over. This comes in tension. The bar does, and this is the compressive part. This stops it from wanting to rotate over the concrete on the underside of the deck, since it's a solid cylinder, if you will. Take a section out and cylinder it, if you will. And now you see, oh, this is why it can't keep rotating over, because it's pushing back against the wall. It has no choice but to stay in that arc because of the PT bar. Let's call it PT bar now. It's the rebar acting in a post-tension capacity, anchored at the ends, with no with the load, if it's stressed at all, meaning if you ring it, if you pull on it and it's taut, then there we go. But if you pull on it or tap on it and it's kind of like loose, all right, well then it's got a lot of redundancy going on in the deck, and it's not, that bar is not active, helping out with this PT effect. But if you pull on it and it's, tap it, bring on it, and it's taut, you go, okay, it's acting like a PT bar at that point. And you can start evaluating different exposed bars just by that technique of what I just described to you. Hopefully this was understandable to you. For you guys that know that the exposure of the decking, um, so here's the wall, and then let's do this is the outer cantilever, and this zone out here is pretty much all good. There's a few fracture parts that are not, but pretty much this zone out there is good. And there's pretty much a zone by the wall that's also good. Okay. And then let's see if I can change colors here. How do I do that? Colors on this one. It's a little different scale, a little different chart. I got multiple things here. Not sure what that does. So between here, okay, go away. So between here, we have the steel. All right. Remember, I'm thinking of it. It's and the spacing is pretty consistent. And in some places, so it's acting as you have the anchor out here. If you look at the evaluate it, you'll see it's pretty much good there. And here's the wall. And this would be the secondary location, back there by the wall again. For the most part, these two zones, zone 1, zone 2, anchor points 1, anchor point 2. So anchor points, right? Where you see the exposed rebar right here is what I'm referring to, that you would attempt to see how it's in tension or is it not in tension. Remember, we have some redundancy because we have cross steel that goes this direction that can help wrap around this steel. Say this section here was loose. Like, well, how's it possible? How's it loose now? How's it not taut and ringing? Well, because of the compressive zone on the bottom side, and also that you can pull the other steel is acting like transfer beam to get it to transfer apart. Let's say like 5 of these are acting a little fishy. Well, the steel below is able to transfer the loads across and start picking up in these other bars that are on the outer end. All right, so it starts picking up out here, and these bars are the transfer steel that get it to it, the crossbars. And again, remember the bottom part of the deck is in compression back to the wall. We do not observe any real spalling there. So this becomes, again, like, think of it like a PT bar, post-tension bar that has anchorage, but it's never been, you can't crank it up. You can't add more tension to it to help with this. It's just exactly this anchor points. Again, some of the ends have where the salts of slurry, if you will, have made it into the deck there, have deteriorated some of these ends and spalled off approximately 1 to 2 inches. Looking beyond that 1 to 2 inches back in the deck, you may still see some loose scale flaking back, which now we're looking at, okay, now we're back here. Some of the zones might be back here as opposed to the outside edge. That's on a couple of places that I think I would theorize that you're picking this resupporting back here. There is where there will be some splitting of the concrete. Again, you saw what would happen there. So hopefully this is totally confusing for you and it helps you out. Yeah, of course I don't want it to be confusing, but I want you to see it in a different light now. So you go back to say the structure, and you yeah, I'm trying to think if I can do this. No, I can't. I can't show it to you again. All right, so hopefully that was helpful for you, really to help you understand why the you can see that exposed steel and why it still may be participating because of the anchors zone 1 and 2. And there you have it. It's simple as that. Now, oh, I'm sorry. Before the failure, though, before the splitting of the top surface, and maybe it still has some bottom connection, but this is why it's so critical that that guy stays off that deck. That Brett Kale stays away from the structure because he thinks it's all fun and games, but he thinks it's all fun and games, but check my color. But him bouncing or in this can break anchorage here. All right, we don't, and that's a shock load. You don't want that shock loading there because you can break anchorage more than likely there, or him wherever he's jumping. He can start breaking anchorage. This anchorage it works, but it wasn't designed for somebody to put a human jackhammer to it. So this is why he also needs a restraining order against the deck, against the building for him to stay off of it. His jumping up and down, hitting the steel, ultimately creates a shock load here, and that shock load could cause the anchorage to fail. And the shock load of him jumping up and down can be, you may think it's nothing, but he might be creating 700-800 pounds of local force on a deck that's designed to take commercially 80 pounds per square foot. He then puts 700-800 pounds of local force into one bar, which it was not designed to take. Okay, so all right, love you guys. Hope you understand this video. Not too coded, but let's see if we can go with this. I'm trying to figure out how to get out of here.